Hey, this is Calculus Related Rates Day 2, where I just want to take another look at some different types of examples that you guys will run into. First of all, I made a few statements in class that I want to make sure that everybody is thinking about as we get started on some of these more difficult types of questions. Whenever you come upon a related rate question, recognize that one of the keys here is to identify the rates that are involved. And a person wants to put variables on anything that's in motion and not put variables on things that aren't in motion. After that, we're going to look at these rates and we're going to try to make a connection between the rates using any relationship that we can find. So that's the part of all of this that gets a little bit more obscure and difficult, is to figure out what is the connecting equations that will connect my related rates, so to speak. Okay, so here's a quick example. Apparently this Joey fella is perched precariously on top of a 10-foot ladder, leaning against the back wall of an apartment building. Obviously he's spying, when he starts to slide down the wall at a rate of 4 feet per minute. So I ran into my first rate there. I'm just going to kind of keep track of that. And Joey's accomplice Lou is standing on the ground at 6 feet away. So here's Lou, I guess. This is him. And the question asks how fast, so they're asking a rate, how fast is the base of the ladder moving when it hits Lou? Okay, so you guys have kind of gotten, I think, the hint that I like to lay these out in a very similar fashion every single time. Like, I want to know what are my given and what is it that I'm supposed to find. All right, these are kind of two things that I like to identify in each one of these questions. And each of these questions is pretty much going to have that happen. So we already ran into a rate here. It says that we're seeing this fella here, Joey, slide down the wall. So luckily for us, this particular question already has this labeled. If it didn't have it labeled, I would label it because I have motion happening with the top of the ladder going down the wall like this. So if y is the distance from the floor to the top of the ladder, more or less this rate of that change is dy dt. So they're giving me a dy dt here is 4 feet per minute. Watch out though, you have to catch that if y is decreasing, y is getting smaller because this distance is going downward, then I'm going to want to note that that is a negative 4. So it's falling down at a rate of 4 feet per minute. I just have to check out, hey, it's decreasing, it's getting smaller, and I'm given dy dt equals negative 4. Perfect. Okay, so they're the ones that labeled it y here. I maybe would have called it h for height or something like that. The moral of the story is we want to put variables on things that are changing, and this picture shows that very nicely. The bottom of the ladder is moving out, and the author of the question already put an x on that distance. So this distance, x here, is changing, which means it's an excellent one to apply a variable to. And that is actually the question. We're supposed to find dx dt. I can expect it to be a positive value because x is going to be growing when this happens. Find dx dt when, well, it looks like when it hits Lou. But Lou is 6 foot away, so that turns into when x equals 6. Okay, now as I mentioned in class, we're always trying to find the connecting equation between our variables and our differentials. So I've talked about both of the rates. I can see that my differentials contain an x and they contain a y. It's pretty obvious. The author already had those labeled for me, but I don't want to overlook because just because he had it labeled for me doesn't mean every question is going to be labeled for you. So if I look at this picture, notice that the author already put the 10 foot on the ladder. This is a distance that did not change, and we want to put those in right away. There's no change here. This stays the same all the time. It's a 10-foot ladder no matter how it slides. So I would label that 10 foot and feel free to put that in right away. Okay, but I won't be plugging in x equals 6 right away because if x equals 6, then neither y nor x can change, and I won't get a differential using x or y. Okay, so hopefully that makes some sense. The next part of this question, which maybe it's obvious to you, you're looking at this picture, but it's the part that gets progressively more difficult in section 2.6, and that is to find the equation that's connecting these variables. I think you guys can look at this picture and go, well, Mr. G, you got x, you got y, you got a 10. That's definitely a right triangle. I'm thinking that my connecting equation is that x squared plus y squared is going to equal 10 squared. I think you'd be right about that. X squared plus y squared equals 100 is my equation that's connecting my two variables. But please make sure when you're doing this that before you differentiate, you come up with an equation that only has the variables that you see in your differentials. Okay? So this one's all set. Everything's set. But some of the things to kind of look for this connecting equation. Connecting equation can be just about anything that you see relevant in the diagram. It might be anything you see relevant from past, like volume and area and surface area and all those things that you've learned from the past that you have to draw into the question. Obviously, if you see a right triangle, you're going to think that, hey, I might use Pythagorean's theorem on this question. Definitely, if someone were to start talking about area, volume, you know those formulas. These are all things that you're going to bring in to the question when the question implies that they are somehow valid. Okay, so, but some of those that maybe you're going to forget that are very important is similar triangles. When I mention similar triangles, I'm talking about, how you guys used to do set up proportional reasoning, like AB is to, like A is to B as C is to D type work like that. So we might use proportions. If someone mentions an angle measure, if someone's like, hey, the angle measure is changing, and I all of a sudden look at my diagram and see a theta involved, like I'm sure that as this ladder falls down, this angle right here is changing. So that might be something a person would bring up. If an angle measure is changing, I'm going to start to look at trig problems, trig equations, even just the definition of sine. I mean, I think that's actually valid over here in this question. I didn't think about that. I could ask that question. If they would have mentioned the angle at all, I would have brought in, sine in this picture over here is equal to the opposite over the hypotenuse, y over 10. So, things like that are less obvious, that you have to just bring this stuff in because it is somehow related to the variables that you are trying to connect. So a lot can happen, and that's why this gets a little bit fuzzy as we turn the page and we look at pages 158 and 159 of your book, which I'm going to reference that again, so if you want to pause me and get that open, that's fine. But in this example, I think I'm ready to differentiate. I have only the two letters which I need the differential for. I can just get after it. So it's 2x dx dt. Keep in mind, I'm differentiating with respect to t, which is why I'm using the chain rule on x for a change. Plus 2y dy dt. The kind of neat thing here, or something that is strange, is this is just going to equal 0. So the length of the ladder somehow is just out of this related rates question. In fact, I'm going to divide this whole question by 2, since that algebra is really like screaming at me to do it. So if I divide it by 2, I'm going to get x dx dt plus y dy dt equals 0. And I'm ready to go to work here. They said find dy dt, or given dy dt is -4, so I can plug that in at this point. So I'll do that. I'm going right in here into dy dt. And then dx dt is what I'm searching to find. So I should be all set. I have x equals 6, and I go, yeah, I got this. X equals 6, dx dt is the question. Dx dt, I'll make sure those t's don't look like x's. Plus y, I have that dumb moment where you're like, oh snap, I'm totally missing something here. I know x is 6. I'm not quite sure about y yet. Dy dt is known to be a -4, so I can fill that in. And I can't quite solve for dx dt because currently y is still a variable. Well, at this point in the question, I start looking around. I'm like, what am I doing here? Oh, wait. Now I can nail down that moment. Like the moment when x is 6, I think I can find exactly how long when x equals 6. I think I know what y equals, especially if the hypotenuse here is 10. So again, I'm just going to go back up to my equation and find something I need. Now, it's not like you pragmatically do this on every one of these questions. I ran into a need here, like I have a blank I couldn't fill from the given information in the paragraph. So I basically decide, hey, I'll look around and find a connection. I'm going to substitute what I know when x equals 6 into here. We're going to go 100 minus 36, and this is an 8. So this is basically a Pythagorean triple. So I can solve that if I need to. You know, if you did the 100 minus the 36 square root of, that would be a great way to find y, right? Okay, so anyway, I end up with 8 because it's 64. And I then know that when x equals 6, also y was equal to 8. That happened at the same moment. So I can put that in now and finish solving accordingly. When I get to this point in the question, I look at my results and I ask myself, okay, does that make sense? I ended up with a positive 16 thirds. You know, I added over the 32 and so on and so forth. So if x is a positive value, that means it's growing. That seems very reasonable. So my answer to the question is 16 thirds, or 15 and or 5 and a third, one way or another, a way of rightness. And then I want to label it with the proper units. So it was moving down before in feet per minute, I believe it was. Yep, in feet per minute. So I want to make sure I label my answer with 16 thirds feet per minute. Perfect. That all makes perfectly good sense for this question. And that is the answer to the question. I'll just double check that I did answer that. Yeah, when it hits Lou, it's moving at 16 thirds feet per minute. Okay, now that was a terribly violent example. I'm really sorry that Joey fell there. He is kind of dressed strangely, so I'm not real sure these two characters. But anyway, let's take a look at one that is right from your textbook, and I'll maybe help get you boosted off here and going on this question. If you take a look real quickly on page 158, I think you're going to appreciate that I'm going to help you on this question. I'm just going to try to make a sketch of some of the information that I'm seeing in number 20. It looks like there's some sort of right triangular, or not necessarily right triangle, some sort of triangular trough thing here. So let me get that drawn out. Well, hopefully you managed to get a nice sketch of this in your assignment or wherever you're going to take this down. We are going to have number 20 in the assignment, so it's fine if you did your sketch and are starting this out in your homework set. I don't care if it's a little out of order. But as I look at number 20, I realize just in drawing the diagram everything that's going on, but there's some details in here that the author's kind of given you that I want to double point out, okay? So first of all, he describes the size of the trough as it's shown in this picture. And then it says the ends are isosceles triangles with altitudes of 3 feet. Okay, perfect. It says in part A, water is being pumped into the trough at 2 cubic feet per minute. How fast does the water level rise, or how fast is it rising when the depth h is 1 foot? So he calls it h and he calls it depth, both. They had already included the 2 cubic feet per minute in the actual diagram. So I kind of already had the feeling I knew a given here as a rate. So one of the rates that was given was dv dt. I know that's volume because it's cubic. So dv dt is equal to 2 cubic feet per minute. I'm supposed to find this rate at which the height of the water is changing. Now that's what's a little bit weird about this one, because I told you don't apply variables unless it's changing. And they just go ahead and they describe this trough in which none of the trough is changing. So all of these numbers are static, they're not changing. But the thing is if you pay close attention, what we're worried about here is water. We're not really paying attention to the trough changing sizes. We're looking at how the height of this water, they marked it back here, is changing over time. So they're asking us to find a dH dt when a specific moment happens, and that specific moment in part A is, it says when the depth is 1 foot deep. So when h equals 1. Okay, so there's a few distractors here, or pieces of this that could be a little bit confusing. You know, if you can see the water depth in there that's growing, that's the part we're actually writing a differential equation for. Okay, so we look at this thing, we're like, huh? Okay, they did talk about volume, but it's a real easy thing to go calculate the volume of this trough But that would be completely wrong because we're talking about the water. And that's really important. We're finding volume of water. Okay, so that's kind of the hard part because you're thinking volume and you're like, oh, well, I'll find the volume of the trough. Well, the trough isn't changing, so that would be incorrect. All right, so what do? Well, I look at it and I'm like, well, in terms of the water, what doesn't change? The height's definitely changing as water runs in, but this length back here of 12 matching the trough, that never changes, except for perhaps the first iota of a second it takes to cover the bottom of the trough. But anyway, minute second there, let's not consider that, and I know that this is 12, and let's see, how do I find the volume of an isosceles triangular prism? That's what this thing is. I have water here that is a triangle on the end, and then it's a prism of length 12. Okay, well, I guess volume is the area of the base face, so do I know how to find area of a triangle? Yeah, it's 1/2 BH. All right, so I think that H is the same H that's back there. And then I would take that times the length of my prism here of 12, and that would start to turn this into the volume equation I need, volume of water. But I look around and I'm like, okay, I have a V, I need an H, I have an H, but there's this B that's kind of in the road here that's not what I was looking for. So if I come over here and look in my diagram though, B, what I meant by that was the length of the base of that triangle that's in there. And the kind of drawing and sketching and fumbling around here that I'm doing right now, this is exactly what your homework should look like as you're getting stuck. B is that length there. H is the height of the triangle. I'm trying to find the area of a triangle here, 1/2 BH. Then when I times it by 12, I end up with volume. Okay, so I'm looking at it and I'm like, oh, you know, he did a Pythagorean theorem one, but this is not a right triangle. I know, let's see, I know I need to get down to just V and H, so the letter I want to get rid of is the B. So here's B. How's that related up in here? Oh, maybe you're seeing it as well. I see similar triangles. I have the trough is building a similar isosceles triangle with the end of the water. And that means there is some sort of proportion in here that is going to make me write a relationship. Okay, so let me see if I can break this up. So if B is the width across this blue triangle and 3 is there, I should be able to go B is to 3. So I'm doing the little is to the big as little height. H is to the big height. Oh, the big height was 3. Perfect. Oh, nice. So basically, since the trough had a height that was equal to this base across here, then I should expect it to be the same in my slice of water down here. So if I cross times, in other words, I can see that B actually equals H in this question. Sweet. Well, there's my little helper equation. It ended up being similar triangles. And I'm ready to substitute in to get rid of the letter that I don't want. I don't want B, so my volume equation, I'm going to get it derivative friendly here. I had a 12 and I had a half, so I'm going 6. The B is equal to H, so instead of writing B times B, I'm going to write 6B squared. And this would be my volume equation for the water that's in the trough. Okay, so I think the rest of this question is pretty straightforward, and I will leave that up to you to solve. But you guys get the idea of how you just kind of have to find the connecting equations between the two differentials so that you can go ahead and differentiate in order to solve. I love related rates. I hope you find them as interesting as I do.